All right, so picture this. You walk into a library, right? But this isn't your typical dusty old library. This one's got a special trick up its sleeve.
Oh, like what?
Every single book, see, has its own unique code. You just whisper the code, and poof, like magic, the exact book you need just appears right in your hand. No more wandering around for hours, no more sifting through endless shelves. Just instant knowledge right at your fingertips.
That's a pretty amazing image. And it sounds pretty familiar, actually.
It is, right, because that's essentially the idea behind a hash map.
I see where you're going with this. Hash maps, a way to get the information you need and fast.
Exactly. It's all about speed and efficiency.
Right.
And that's exactly what we're diving into today. Hash maps.
A fundamental concept in computer science, and one that, I have to say, plays a surprisingly crucial role in our digital lives.
Oh, absolutely. And in this deep dive, we're going to, crack the code on hash maps, figure out how they pull off this feat of super fast information retrieval.
And maybe even more importantly, we'll explore why they're so vital to, pretty much all the technology we use every single day.
It's like getting a backstage pass to understand how things really work behind the scenes. No boring textbooks required.
Right, because once you understand hash maps, it's like you suddenly see the hidden gears turning in all sorts of digital systems, from databases to websites to, even machine learning.
So how about we start with the basics? Like, how does this magic library system actually work in, the real world of computers?
Well, the real star of the show is something called a hash function.
Hash function. This is our super smart librarian who comes up with those unique codes for every single book.
Exactly. It takes the key, that unique identifier for each piece of data, and it kind of scrambles it up in a specific way to create an index.
An index. So that's basically like an address within a huge digital storage space, right? Kind of like telling you, okay, the book you want is on this row in this shelf number.
Exactly. Now, this hash function, it's got a pretty important job. It has to be really, really fast.
Mm-hmm.
We want instant retrieval, right?
Right. We don't want any lag.
Absolutely. And it also needs to be predictable. In computer science terms, we call that deterministic. So that means if you give it the same key, it should spit out the same index every single time.
Makes sense. Otherwise, it'd be chaos if the same book code kept sending you to different shelves every time you used it.
Right. And ideally, you also want this function to spread out the keys as evenly as possible across those digital shelves.
Even distribution. Now, why is that so important?
Well, think about it. You don't want all the books piled up on one shelf, right? It makes finding things much slower. The same goes for data. Even distribution ensures that things run smoothly and efficiently.
Makes sense. But here's the thing, right? Sometimes, no matter how clever our digital librarian is, there's a chance they might accidentally assign the same index to two different books.
Two different keys ending up at the same address. We call that a collision.
Collision. Sounds a bit like a digital traffic jam. So what happens then?
Well, thankfully, there are some pretty smart ways to handle this. One common method is called chaining.
Chaining, so like a chain of books.
Sort of. Imagine that at each index in our storage space, instead of just one book, we have a little chain of items. All of them got assigned the same initial index, but they're linked together in a list.
So when you're looking for a specific key, you go to the index and then just scan through that list until you find the one you're looking for.
Exactly. It's like those old library card catalogs where if multiple books had the same subject, you might see a longer list of numbers to check. It's an extra step, but it keeps things organized.
I get it. But is there another way to deal with collisions? What if you don't want to use chaining?
Well, there's another technique called open addressing.
Open addressing. So like finding a different shelf if your first choice is full.
Precisely. It's like trying to find a parking spot in a crowded lot. If your first choice is taken, you simply move on to the next one and so on until you find an empty space.
So even though collisions create a bit of extra work, these methods keep the system running smoothly.
Exactly. Because the real magic of hash maps is how quickly you can get the information back. Once the key's been transformed into its index, retrieving the value is lightning fast. We're talking constant time complexity here.
Constant time complexity. That sounds pretty technical.
It is a bit. But what it means is that the time it takes to find something in a hash map stays pretty much the same, whether you've got 10 items or 10 million.
Wow. So it doesn't really matter how big the library gets. You can still find any book in the same amount of time.
It's incredibly efficient, and that speed is essential for a lot of things we take for granted. Like, think about searching for a word in a digital dictionary.
Or imagine logging into a website with millions of users. The system needs to verify your username and password super quickly.
Hash maps make that possible. They allow for those millisecond-level searches through a potentially massive amount of data.
So speed is a huge advantage. But are there any times when using a hash map might not be the best approach?
You're right to ask that. It's not a one-size-fits-all solution. For instance, if you need to keep your data in a specific order, hash maps might not be the best choice.
Because the hash function mixes things up, right? So there's no guarantee that the order you put things in is the order they'll be stored.
Exactly. If order is crucial, then other data structures like balanced trees might be a better fit, even if they're a tiny bit slower on average.
So it's always about choosing the right tool for the job. But okay, we've talked about how hash maps work and why they're important, but where do we actually encounter them in the real world?
Oh, they're everywhere. You probably interact with systems that use hash maps every single day without even realizing it.
Like where? Give us some examples.
Well, take database indexing, for instance. When you search a database, you're asking it to find specific information in a huge ocean of data.
And hash maps help speed up that search.
They're often used to create indexes, which act like those magic book codes we talked about earlier. So instead of looking through every single entry, the database can jump straight to the relevant data.
And then there's caching, which we briefly touched on before. It's all about storing frequently accessed information in a temporary space, so you don't have to fetch it from the original source every time.
Hash maps are perfect for caching because they're so fast at retrieving that data. Think about loading a web page. A lot of the elements you see might be coming from a cache powered by a hash map.
Makes sense. So the page loads faster because it doesn't have to download everything from scratch every time.
Exactly. And then there are things like autocomplete systems. You know, when you start typing a search in Google and it suggests possible completions.
Oh yeah, like it's reading my mind.
Well, not quite mind reading, but hash maps are involved. They can store a huge dictionary of search terms and then instantly suggest the most likely ones based on what you've typed so far.
It's amazing how much of our digital experience relies on this behind-the-scenes efficiency. Even something like how internet traffic is routed.
You're right. Routers, which direct data packets across the internet, use hash maps called routing tables to quickly figure out the best path to send those packets. And it all happens in a fraction of a second.
It's like a super fast GPS for data.
You could say that. And then, of course, there's scalability. As the amount of data we generate keeps growing, we need systems that can handle that growth without slowing down.
And hash maps are perfect for that because their access time stays pretty consistent even as the data size balloons.
Exactly. That's why they're so crucial for systems that handle truly massive amounts of data, like, say, search engines or social media platforms.
Yeah, here's something that might surprise some people. Hash maps also play a big role in machine learning.
It's true. They're not just about managing large data sets. They're actually involved in the learning process itself.
How so?
Well, for one thing, they can be used for feature mapping. When you're training a machine learning model, you often have a ton of features, which are basically different characteristics of the data.
Like if you're training a computer to recognize cats in pictures, the features would be things like pointy ears, whiskers, a tail, and so on.
Exactly. Feature mapping is about transforming these features into a format that the model can use effectively.
And hash maps can help with that.
Absolutely. By storing these transformations in a hash map, the system can look them up quickly instead of recalculating them every single time, which saves a lot of time and processing power.
It's like giving the machine learning model its own cheat sheet so it can learn faster.
That's a great way to put it. Hash maps can also be used to cache intermediate results during the training process. You see, machine learning models often go through many cycles of training, and some calculations might be repeated multiple times.
So by storing those results in a hash map, you can avoid doing the same work over and over again.
Exactly. It speeds up the entire process. And even after a model is trained, hash maps can be used to store and retrieve specific parts of the model, or even entire pre-trained models.
So they're involved in pretty much every stage of the machine learning process.
They really are. It's fascinating how versatile they are.
Okay, so we've covered a lot of ground. Let's bring it back to something everyone can relate to. How about social media? Let's say you're scrolling through your Instagram feed.
A perfect example. You open the app and boom, you see posts from all the people you follow. But how does that happen so fast when there are millions of users and so much content being shared every second?
It's like magic almost.
It might seem that way, but hash maps are working behind the scenes to make it happen. Remember how every Instagram user has a unique ID?
Right, like their username?
Well, when you open your feed, the app needs to grab the latest posts from all the accounts you follow. Instead of searching through the entire database of posts, which would be incredibly slow, it likely uses hash maps to quickly access the profiles of each user you follow.
Using their ID as the key to find their profile.
Exactly. And then it might use another set of hash maps to retrieve their most recent posts. This way, the app can assemble your personalized feed in the blink of an eye.
So hash maps are the reason my Instagram feed loads so quickly, even though there's a massive amount of data involved.
It's a key part of the process, for sure.
It really is incredible how these seemingly abstract data structures play such a crucial role in making our digital lives so smooth and seamless.
They're the unsung heroes of the digital age. So, to sum up our deep dive into the world of hash maps, their key strengths are efficiency, speed, and scalability.
And that combination makes them essential for a huge range of applications.
From simple things like spell checking to complex things like search engines and machine learning, they keep our digital world running smoothly.
It all comes back to that magic library analogy, providing near instant access to the information you need, no matter how vast the library is.
And that brings us to a final thought for our listeners. As you go about your day-to-day, try to notice how many times you interact with systems that are likely powered by hash maps.
From searching online to checking social media to using apps on your phone, they're everywhere.
It's a fascinating exercise to realize just how pervasive this fundamental concept is in our digital lives.
And how much we rely on it, even if we're not aware of it.
It's a testament to the power of clever algorithms and efficient data structures to shape our modern world.
And that's a wrap for our deep dive into hash maps.
Thanks for joining us.
Until next time.